A polyatomic ion is a group of atoms that are held together by covalent bonds, and we're going to actually learn how to draw these polyatomic ions and draw what we call Lewis structures today. And so usually we see a charge of some sort at the very top here on the right, and we know that that means when it's negative it's gained electrons, when it's positive it's lost them. So we're going to use that when we start to draw our structures. Now, when we start drawing Lewis structures, you have to understand atoms can make, when they're covalently bonded, can make one, two, or three types of bonds in between the two atoms. So a single bond we're going to see is drawn with a single line, and it's a covalent bond where two electrons are being shared by the two atoms. So the hydrogen brings one atom and the other hydrogen brings an atom, and then they share them when we draw a line to indicate two electrons being shown there. Now we're also going to draw double bonds, and double bonds are, again, 2 electrons per bond, so it's 4 overall, and then a triple bond, same thing, 2, 4, and 6. Now, there is a relationship between bond length and the number of bonds. So you can see here we have a carbon-carbon bond, and when it's single bonded compared to triple bond, we see a triple bond being a lot shorter of a bond. So when we have more bonds, such as a triple bond, it doesn't go any higher than that. The atoms are held a lot closer together than a single bond would be. Before we start to draw Lewis structures, we're going to draw Lewis dot symbols, which is just like individual atoms, and then we're going to put them together to draw Lewis structures. And so this is a notation that we use to indicate the valence electrons and how many there are, and then we're going to go ahead and connect them with other atoms to kind of realistically figure out what an atom or a molecule looks like. Now, to do this, you need a periodic table, and you need to, again, remember the rule for valence electrons. Group 1 has 1 valence electron, group 2 has 2, group 13, so go all the way across there to boron, has 3, and then 14, 15, 16, 17, and 18, they go up by 1 valence electron, okay? So sulfur is in group 16. It has 6 valence electrons. Now, when we draw a Lewis structure here, or a Lewis symbol, we first put an electron on each side, okay, because they want to be as far apart as possible. And so there's 4. And then when we need to, we double them up. So 5, 6. And it doesn't matter what sides you've doubled it up on. I always just do the top or the side, so it doesn't matter. So this is the Lewis symbol for sulfur. Let's do another one. We have fluorine. Fluorine's in group 17. It has 7 valence. So again, we're going to put 1 on each side first. 1, 2, 3, 4, 5, 6, 7. Okay, so that you can see that it has 7 valence electrons. Calcium is only 2. So we're just going to put 2. Again, it doesn't matter if you put top, bottom, side, side, as long as they're not together unless they need to be doubled up. Now, how to put these together to draw what we call Lewis structures. So you're going to learn how to add up all the valence electrons. That is always step 1, so you can figure out how many dots you need in your picture. Step 2, find your center atom. If carbon is in the molecule, carbon is always, always, always your center atom. Okay, and we're going to talk about if you don't have carbon, what you're going to do. Use a pair of electrons to form a bond. So just like I showed you, a single bond has 2 electrons, and you connect it to make a bond. And then any remaining electrons we put on outer atoms, and then any extra than that go on the center atom. And then we will multiple bond if we need to. Now, these steps are hard to understand, so I'm going to go ahead and demonstrate it to you many times over so that you can kind of see how it works. Now, a couple terms just to make sure we're all on the same page here. A bonded pair is just another term for a bond, and a bond usually looks like it's 2 electrons. Now, we typically draw it as a line, and we don't see these dots here. So it ends up just being a connection, but we know a line is made up of 2 dots, and that is a bonding pair or a bond. And then unshared pairs here are what we call more so lone pairs. So this fluorine on the left has 3 sets of lone pairs, and so 1 bond and 3 lone pairs on each of the fluorines, just so that we start to talk about terminology and we can use the correct terms. All right, let's go ahead and draw our first Lewis structure. So step 1, calculate how many valence electrons there is going to be in this entire molecule. So to do that, we're going to add it up. So carbon is in group 14. There are 4 valence. Hydrogen is in group 1. There's 1 valence, but there's 4 of these molecules. So you go ahead and multiply by how many. So this is 4, and then you add up another 4. So our total count for this is 8. Now, second step, you're going to want to kind of place your atoms around. No lines, just kind of arbitrarily placing them. So again, I told you our center atom is always carbon if it exists. So carbon here in the center, and then we can go ahead and just kind of place our other atoms around. Do not connect yet, just draw the atoms. Now, we need to use all 8 electrons. So that's when we're going to now connect the center atom to the outside atoms. So I like to draw them as dots and not lines, because if you start using lines, you're going to not count correctly. So right now I've used 2, 4, 6, and 8. Now, once I have 2 dots, I can connect them and make a line, and it doesn't matter if they look a little funky there. It's just a nice reminder that a line is made up of 2 electrons. Now, we need to then see, is everything satisfied? When I say satisfied, I mean has 8 bonds, or 8 electrons around. Now, there are some exceptions. Hydrogen is one of those. We'll add to our exceptions list here. Hydrogen is very small, and so therefore hydrogen only wants 1 bond, and that's what makes it satisfied. Now, other atoms, including carbon, always need 4 bonds. And so everything else needs 4 bonds or 8 electrons around it. So let's just make sure everything's good with carbon here. Carbon has 2, 4, 6, and 8. Okay, therefore carbon is happy. Hydrogen only wants 1 bond, so hydrogen again also has 1 for each of these, which satisfies both of them. So this is our Lewis structure for CH4. Let's do this again. So we have CCl4. So carbon again has 4 valence. There's only 1 carbon there. Chlorine has 7 valence, and there's 4 of them. So we're going to go ahead and do 7 times 4 plus another 4. So we have 32 electrons total. Now that's a lot more, but I'll show you where they're going to be placed. So center atom, always carbon if it exists. And then let's go ahead and just place our other atoms around here. And in this case, it's 4 chlorines. Now we next step is going to be connecting our center to our outer. 1, 2, 3, 4, 5, 6, 7, 8. We've only used 8. Now, we need to use all 32. You will always use everything you have. Now, the difference with our first structure is that hydrogen was happy with only 1 bond, but chlorine right now isn't, because it needs to have 4 bonds or 8 electrons around it. So to do that, we need to utilize our extra electrons to fulfill the outer ones. So we've used 8. 9, 10, 11, 12, 13, 14, 15, 16. So you're going to keep filling this in. They each get 3 sets of lone pairs, and then that extra bond they're connected to carbon with will fulfill their 8. So let's just do a quick check here. So again, chlorine is one that wants, everything wants 4 bonds or 8 electrons around it, except so far hydrogen. So carbon is happy, 1, 2, 3, 4 bonds. And let's check one of the chlorines because they're all the same. 1, 2, 3, 4, 5, 6, 7, 8. So remember, when it's a bond, which I'm actually going to go ahead and make these direct lines here, they are made up of 2 electrons. So everything is fulfilled, and I have utilized all my electrons. Therefore, that is CCl4. Okay, ignore those orange marks on there. That was just to show you how many the count was. All right, let's get into some that are a little bit more difficult. We have PBr3. So P has 5 valence, and Br has 7, and there's 3 of them, so 7 times 3. So we have a total of 26 electrons here. Now, I told you if carbon is in the molecule, carbon is our center atom, but carbon is not in the molecule. So in that case, you want to pick the atom that is furthest from fluorine. Furthest from fluorine, okay? So if you don't have carbon, you pick the center atom that is furthest from fluorine, the least electronegative atom. Now, in this case, that is going to be phosphorus. Now, it's also usually the one that's going to make it the most symmetrical. I can't say that 100% of the time, but in this case, if you put a P in the center, you can place your BRs around there, and it's pretty symmetrical. Nature tries to be symmetrical if possible. All right, so I did my count. I went ahead and found my center atom and I placed my other atoms around. Now I'm going to go ahead and make connections. Please make your connections 2 dots before you make them a line, because you will forget that you're counting. So 2, 4, 6. I connected my centers. Now I need to fill in my outers. The reason why is because everything needs outer electrons except hydrogen. So I'm going to keep going here and filling everything in. Again, these are called lone pairs. All right, now, so far if I do a quick count, I have only 24 and I need to use 26. And so this is another rule. After the outers are fulfilled and you have also connected the center to the outer atoms, if you have extra electrons, they are placed on your center atom. Okay, and we call that a lone pair on the center atom. So this is the Lewis structure for PBr3. Let's do a quick check to make sure everything has its fulfillment. So I'm going to go ahead and do phosphorus. Phosphorus has 1, 2, 3, 4, 5, 6, 7, 8. Okay, phosphorus is happy. It has 8. Bromine, which is all the same, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so both of them, or actually all of them, are fulfilled. They have all the electrons they need. Let's keep going here. We have H2O, so let's go ahead and do our electron count. H, there's 1 of them, but there's 1 valence, but 2 hydrogens. Oxygen, there are 6 valence. And so when I add that up, I'm a total of 8 again. What's my center atom? It's the furthest from fluorine, but it is never hydrogen. You can never have hydrogen as a center atom. So I'm going to go ahead and write that. Never have hydrogen as a center atom. Okay? So my center atom here is oxygen. So let's go ahead and put it around here. And let's try to add it on. 1, 2, 3, 4. Hydrogens don't need any more. So hydrogen's fulfilled. Now, remember, extra electrons, when you have them and the outers are complete, which they are because they're really small, hydrogen only needs 1 bond, we go ahead and we place them on the center atom. Now, we don't ever want to place them like this where they're doubled up. Okay, you want to place them as far apart as possible, kind of keeping in mind the 4 planes, north, south, east, and west. So now, let's do a quick count. 2, 4, 6, 8, okay? And those hydrogens are happy, and so everything is fulfilled, and this is actually the structure of what water looks like. This is what a water molecule looks like. All right, so let's go ahead and do a couple more. We're going to draw the Lewis structure for ClO2-. It is a little bit confusing if this is an I or a Cl. Please don't hesitate to ask me if you ever have a question on an exam. It's typically a Cl. I don't oftentimes do a C and an I because it is very confusing. So we have ClO2-1. So Cl has 7 valence and O has 6, and there's 2 of them. And then, so that gets us 19. And then after you're done doing the overall count, you're going to deal with the charge. So the charge on this is a -1. That means there's -1 or 1 additional negative charge. So that means we've added an electron. So therefore we have to do the opposite of what this charge says, -1. We're going to add 1 to our total count. So this molecule is going to have a total of 20 valence. Now, a good tip is your valence is always going to be, your total Lewis structure count is always going to be positive. There are a couple molecules that are negative, but we're not going to be dealing with those in this course. So if you get a negative total count, you've done something wrong. Now, this one has a center atom of chlorine, and again, some of them are very weird exceptions that you'll learn about as you go further into chemistry. So if it is something that the center atom isn't what you would expect, utilizing my rules, then I will just give you a little hint of what the center atom is by telling you. Okay, so trust me on this one, the center atom is chlorine. So then we're going to go ahead and make our connections. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. Now, I've used 16. My outer atoms are fulfilled, and I still need to always use my total count. Always, always, always. So therefore, when everything's fulfilled on the outers, we add the extras to the center atom. Okay? And that's what ClO2-1 is. Now, when you are drawing what we call a polyatomic ion, we indicate the extra electron added or removed by putting brackets up. So therefore, we're going to put a -1 or a 1-, same thing, outside in the brackets around your Lewis structure. So only things that have an overall charge, and then you just write that overall charge over up in the top corner. Okay? All right, CO2. This is going to introduce us to multiple bonds. So let's do our electron count. 4, 6 times 2. So we have a total of 16 electrons. Center atom is carbon. If carbon exists, we're going to go ahead and put our O's on either side. I'm going a little quicker here because we've been doing quite a few examples at this point. So I'm going to make my connections, then I'm going to go ahead and fill in my outers. Please follow these steps in the order I've taught it. There's many ways I've done this, and over the years, this has been the best method. So draw it out, count your atoms, connect your center to your outer, fill in your outer, and then if you have extra electrons, deal with them then. So at this point, I have used all 16, but we have an issue. And so what we need to do is look at each atom and make sure they are fulfilled. They have their octet. Unless they're hydrogen, that's our only exception so far. So oxygen has 1, 2, 3, 4, 5, 6, 7, 8. It's happy. This oxygen has 8 as well. It's also happy. The issue is this carbon currently only has 4. Okay, so because it has 4, we need to do something about that. And so when you have run out of electrons, completely run out, you've used all of this, then we have to do what we call borrow. And so to do that, we are going to actually erase one of the lone pairs and we are going to shift it and make it now what we call a double bond. Okay, so we do not use extra electrons to create a double bond. Okay, double bonds are one that are taken from something else. So people will start to throw double and triple bonds all the time. Double bonds are at the very end after you've checked everything, you've used all your electrons, and you're still lacking an octet. Now let's check carbon again and see how carbon's looking. So carbon has 1, 2, 3, 4, 5, 6. Carbon still needs 8 electrons. So what we're going to do is go ahead and steal it again. And we're going to go ahead and move it over and make another double bond. So it's symmetrical. Now, does this do anything to oxygen? Let's check. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is still fulfilled. It doesn't matter that it was a lone pair and now it's a double bond. It's still being shared. So now this is how we would draw CO2. Okay, so it has a carbon double bonded to oxygens on either side. Now, do you need to move your lone pairs to the top and the bottom? You do not. Okay, you can leave them how they are. They don't have to be opposite ends, and you don't have to spread them out. Once you've drawn them, they hang out in pairs in the Lewis structure format. Okay. Now, a couple exceptions. We've already talked about hydrogen only needing 1 bond. There's going to be a couple extras here. Beryllium is so small as well, it only needs 2 bonds. And remember when I say 1 bond, it's 2 electrons. 2 bonds only needs a total of 4 electrons. Boron is also pretty small. It only can hold 3 bonds or 6 electrons total around there. So these are the only ones that are going to be a deficit or less than 8. Okay. Things that can increase above 8 only if they need to. Only if they need to. That's a big caveat here. People will start adding extra if they feel like they need to. Is P. P can have a total of 5 bonds if need be. S can have a total of 6 bonds. And then Cl can also, if it needs to, have 6 bonds. Remember when I say 6 bonds, that's 12 electrons, 5 bonds, 10 electrons. And then anything with a 3D in its electron configuration can actually expand up to 6 bonds. And remember, that's because that 3D, when it starts to get filled, it provides a lot more space on that, in that 3D or 4D or 5D orbital, which allows for a lot more connections to be made between the electrons, and then the sharing is, opened up more. Now, things only expand if they need to, So if you have extras and you have nowhere else to put them, then you can expand them. And I'm going to go ahead and show you a couple examples here below. Now, again, I kind of just mentioned this, but I wanted to write this down. There are many more examples of central atoms that that can deal with more of an octet, because elements of the third period, so the third period is the horizontal third period down, and beyond that have a D subshell, right? They start with 3D. They can expand their valence shell electron configurations, which then allow a lot more connections. Now, there are a couple of exceptions that are above the third period, and we discussed them being S, P, and Cl. So let me go ahead and show you what some exceptions are. So I told you B is an exception. It only wants 3 bonds. So let's go ahead and calculate this. B has 3 valence. F has 7 times 3. So 21. So total of 24 electrons. My center atom here is going to be the furthest from fluorine, which is definitely boron in this case. So I'm going to go ahead and draw the electrons. I'm going to go ahead and connect the center to the outers. Now you can leave them as dots. I usually fill them in to make a line, but you could leave them as dots. It doesn't really matter. And then I'm going to go ahead and fill in my outers because everything needs 8 electrons around except hydrogen. And so therefore I went ahead and used all 24. If this B was not an exception, I'd have to borrow and make a double bond if it was something else. But B is an exception, so this is all it needs. It's happy with just 1, 2, 3, 4, 5, 6, okay, or 3 bonds because it is a very small atom. All right, then we have BeH2. So again, Be is 4 valence. Oh, excuse me, it's actually 2 valence. Hydrogen is 1 times the 2, so a total of 4 electrons here, a very small molecule. H is never my center atom here, and I'm going to go ahead and just connect this. And this is that easy, okay? So these are ones that we have say that they are satisfied with a deficit of electrons, a deficit of 8. And then we also add hydrogen to this list, and remember that only needs 1 bond. Now let's do some more obscure ones here. So we have HCN. So let's go ahead and count our electrons. 1, 4, and then 5 here. So our total is 10. My center atom is always carbon if it exists in the molecule. So I'm going to go ahead and just place this in a row. So it's not always going to be symmetrical, okay? In this case, C's in the center, and then we have an H and an N. I'm going to go ahead and make my 10 electrons. Now, hydrogen can't take any more. It only wants 1 bond. So I'm going to go ahead and connect this side, but nitrogen does need 8. So I'm going to go ahead and fill that in. And so right now I have currently used all 10, but the problem is this carbon only has 4 electrons or 2 bonds, and carbon can never, ever, ever, ever have more than 4 bonds or less than 4 bonds. Never, ever, ever. Carbon is not an exception in any case. So now when this happens, what you have to do is start to do that thing we did with CO2. We have to erase and borrow. So I'm going to go ahead and erase a pair, a lone pair, and I'm going to move them over and create a double bond. Now, does that satisfy carbon? Let's see. 1, 2, 3, 4, 5, 6. It does not. But I can't take any from hydrogen, right? There's nothing I can do. Hydrogen doesn't have any lone pairs. So I actually need to steal again and go ahead and make a triple bond. So this is our first example here of a triple bond. So carbon now has 2, 4, 6, 8, and nitrogen also has what it needs, 2, 4, 6, 8. Okay, so this is HCN. Let's do SO4 minus 2. This is a total of 6. This is a total of 24. And so then 32. And then add 2 extra. We're at 34 here. Let me make sure that's right. 6 times 5. 30, 32. Yeah. Nope. I'm incorrect. Counting the electrons is the hardest part there. Excuse me. Okay. Now, center atom. Center atom is usually going to be the thing that makes it the most symmetrical. In this case, it's going to be the S. And I'm going to go ahead and place my 4 O's around here. And then I'm going to go ahead and make my center connections. And then I go ahead and fill in my outer electrons. All right, now let's do a quick check. All the S's and the 1S and all 4 O's have everything they need. Everything is fulfilled. And then we don't want to forget that when we have an ion, we put brackets around it and we write the charge outside. Okay, that is the Lewis structure for sulfur. Now, let me show you an example of what students will sometimes do. They will remember that I said sulfur can have up to 6 bonds. So then students will start stealing and double bonding and doing all this crazy stuff. Please do not do that. If it is satisfied and there's no extra electrons, then you can stop with just 4 bonds. It prefers to be only 4 bonds. Now, if you had extra electrons here, you had to make a lone pair on the center atom, but we don't. Okay, so we're just going to go ahead and fulfill this with 4 bonds. It does not have to expand. It is fine with just always 4. All right, now we have carbon, 2 fluorines, and 2 hydrogens. So we have 4, we have 14, and we have 2, 1 times 2. And so we have 14. Okay, we have a total of 20. Carbon is my center atom. Now, it does not matter where you put the H's and the F's. You could have put them the complete opposite area as I put them. It doesn't matter. You could put them together on the top and the side. There's no preference with that right now. 21, 2, 3, 4, 5, 6, 7, 8. Hydrogens don't need anything else, so we're going to go ahead and fill in the outers. Okay. And then we do a quick count. Fluorine has all the bonds it needs. Carbon has all the bonds it needs, and we are done. Okay, so it looks a little bit weird, but remember, hydrogen's so small it can really only fit one bond. We're going to keep going with some more examples here. We have SO2, so sulfur is 6. And again, you're welcome to pause the video and try some of these on your own and then check your answers. So we have 12. We have a total of 18. Okay, so my center atom is going to be sulfur. 2, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. Now, again, I've used 16 up, but I have a total of 18, and I have to use them all. So I'm going to go ahead and place that on my center atom. Any extra after everything's filled goes on the center atom. Now, the issue here is sulfur currently only has 2, 4, 6. Sulfur needs to have 8. Nothing can be less unless it is beryllium, boron, or hydrogen. Now, of course, there are more exceptions. That's the only ones you have to memorize. So what we're going to do is we're going to steal. This is the only time stealing is going to be okay. We're going to steal it, and we're going to go ahead and double bond it. Now, I know you're going to say, do I have to double bond the other side? No. Okay. Sulfur, therefore, has 2, 4, 6, 8. It's happy. You do not want to just start double bonding for no reason. Even though it's not symmetrical, that's okay. That's just what it's going to look like. All right, so COF2, we have 14, we have 6, we have 4, 10, 24. Carbon in my center, I have 1 oxygen and 2 fluorines. So remember, if carbon's your center atom, don't overthink it. Okay, now, we are going to look at this molecule and say, okay, we've used all 24, right? But the problem is carbon only has 1, 2, 3 bonds. Now, from personal experience, I know that the oxygen is going to actually give up its electrons to make the double bond. But at this, I will tell you that if you were to instead make this in blue, erase this and make this a double bond and keep the O a single bond, perfectly fine. There would be no problem with that. Okay, I just know oxygen tends to make double bonds, so I just steal from there to create the double bond. But if you created the double bond on just either of the fluorines instead and kept carbon a single bond, your answer would be perfectly correct. Okay, until you end up learning what we call formal charge, which could come further in your chem career. So that is COF2. And again, why did we have to double bond? Because carbon only had 1, 2, 3, 4, 5, 6. Carbon never can have more or less than 4 bonds. It has to only have 4. Okay? All right, NO2, or N2O, excuse me. So we have 10 here, and then we have 6 here, so we have a total of 16 electrons. I'm going to go ahead and make my center atom the O, and I'm going to go ahead and put the ends on either side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. Okay, now that looks good for nitrogen, but the oxygen is unhappy. You can see that it only has 2 bonds, so I'm going to go ahead and erase this side and make it a double bond here, but oxygen still doesn't have enough. Now, when the question is, do I triple bond one side or do I double bond both sides? You're going to double bond both sides if it's possible. For example, that previous example with the HCN, H couldn't make any more bonds, so I had to triple bond that side up on the previous page. But in this case, I could double bond either side, so it makes it more symmetrical. Nature always prefers symmetry if it can have that. All right, I promise, I think we don't have too many more examples here, but these are more exceptions. These are ones that can increase above 8. So let me show you how and when you would know to do that. So P has 5, Cl has 7 times 5, so I'm just going to make that 35. Total of 40 electrons. P is my center atom. It's going to make it the most symmetrical. Go ahead and place your Cls around here. And then nothing's new here. Make your connections. Now, remember I said P can expand up to 5 bonds. This is a case where it has to, right? Because you have 5 Cls and they all have to connect to the center atom. So this is the case where you would see an exception being necessary, and there's really no other way around it. Okay, that is PCl5. All right, let's try SCl4 here. So we have 6, and we have 7 times 4, 28, 34 electrons here. Okay, S is my center atom, Cl, 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 Cl. Please try to make them kind of the top, as far apart as possible when you're drawing those outer atoms. All right, so I'm going to go ahead and kind of quickly roll through this because we've been doing this same step, but you're going to see a new step at the very end here. So I've fulfilled all my chlorines, and my sulfur is actually fulfilled as well. But the problem is right now I've only used 32, and I have to use 34. So if I still have extra electrons, just like we've previously done, you put them on the center atom. Now, the way you put them on the center atom is kind of on a catty corner. So please, I don't want to see them. I'm going to take those away. I don't want to see this. Okay, you don't put them on opposite ends. They become a lone pair. I don't want to see this. You don't put them like that. It's like an extra bond. No, you put them like kind of up in the corner and you put them next to each other. Okay, and you could put it on any of the corners. Sometimes people will draw kind of a little circle around them. You're welcome to do that as well, just to kind of make it evident. Now we've used all 34. So you can see when it's necessary to expand because you have extra electrons and there's nothing else to do with them. So that is when you have to expand. All right, let's do BrCl3. So Br is 7 valence and Cl is 7 as well, so 21. So we have a total of 28. My center atom is going to be the Br in this case, just to make it the most symmetrical. Okay, I'm filling my Cl's around, and I'm still right now only have 24, but I need to use 28. So I'm going to go ahead and put my extra electrons on the center atom. They don't go anywhere else. Extra electrons never, ever, ever become double or triple bonds. Students will get extra electrons and then start throwing double and triple bonds everywhere. Double and triple bonds are only borrowed from a lone pair of another atom. Extra electrons go on the center atom. Please make yourself a note of that. All right, to finish this up, we're going to go ahead and look at resonance. So we have a structure here, NO3, and we have the Lewis structure. And so let's just take a quick look. We have our N center atom. We had 24 electrons, and this is 3 ways to draw it. Now, you can see here we have a double bond to this O that has 2 lone pairs, and we have 2 single bonds. The center one has a double bond on the top left and 2 single bonds, and the one on the right has a double bond on the right and 2 single bonds. These are all 24 electrons, 2 single bonds, and 1 double bond. These are all exactly the same, okay? They're just drawn whatever choice you chose, basically whatever decision you made to put that double bond on, whichever O you prefer. In real life, though, okay, we call this resonance. Resonance means that because this double bond could go on any of these, what it's doing is actually constantly fluctuating between all of these. And the way we do this is we draw it as many ways as possible, and then we draw these double-headed arrows in between the structures to indicate that this double bond is not stuck here all the time. Instead, it's constantly moving between these 3. We actually say these are kind of like 1.5 bonds for everything because it's shifting so fast that it's like sharing it with all the different N to O connections. Okay, so resonance, again, it has to be to the same atom. If one of these was like an F or something like that, that's not resonance. It's when it's the same atom. There could be 2, there could be 3 structures of resonance, but you draw them all and you put double-headed arrows between them. Okay. Now, what happens when these electrons are, so this is another example of resonance. You can see here, this is O3, this is ozone, and we see the double bond over here, and then we see a double bond on the right side. And again, there's only 2 structures, and we do a double-headed arrow to show that. And what is happening here is these electrons that are moving, I'm going to go ahead and kind of like draw them here, they are actually called delocalized. So what is happening is they are fluctuating, and they then in between move over here, and they're shifting in between. You don't have to draw this, I'm just showing you. So they're delocalized, meaning they have a little bit more movement than normal electrons. So in resonance, the electrons that are moving to create that double or triple bond that's constantly fluctuating, we call those delocalized.